Hello, I am Alexander Kovalyev, and today I want to talk about input-space optimization for neural networks-based forecasting of non-stationary time series. Economic crises, conflicts, pandemics, and climate change disrupt time series patterns, reducing the accuracy of classical forecasting methods. These traditional approaches assume stationary data and struggle with structural breaks and external shocks. Recent research emphasizes the need for models that incorporate internal influences to adapt to non-stationary conditions. Modern machine learning and neural networks offer flexible tools for capturing nonlinear patterns and complex dependencies in such data. Various neural network architectures have been explored, but most studies prioritize model design over understanding the role of external factors. Ignoring exogenous variables often leads to poor forecasting performance, especially in unstable environments where external influences strongly shape outcomes. This study focuses on improving forecasting in public health by integrating external factors into the model input space, enhancing reliability without merely increasing model complexity. This paper examines the integration of exogenous variables in public health, especially the spread of infectious diseases, which is highly sensitive to external factors, including seasonal factors, population mobility, demographic changes, public health measures, and emergencies. Under these conditions, disease dynamics can deviate significantly from historical trends, making traditional forecasting approaches unreliable. The scientific challenge is to develop optimization-oriented forecasting approaches that improve accuracy and reliability through rational structuring of model inputs and integration of relevant exogenous variables without increasing model complexity. The application of this approach will be explored in epidemiologic forecasting to support evidence-based decision-making in healthcare system. The proposed approach focuses on organization and selection of input information rather than on modifying model architecture of or retraining processes. The experimental base of the study consists of time series data. Data processing includes the removal of missing or anomalous values, temporal alignment of observations, normalization of numerical values, and transformation of the data into a format suitable for neural network training. All these time series are aligned on a unifying temporal scale and divided into training and testing subsets. Additional information is reserved by a set of variables, where each variable corresponds to an independent source of information potentially affecting the dynamics of the target time series. Observed values of these variables at time are represented by the vector. Complete input representations available to the forecasting models at a time is defined as the formula shown on the slide. Using all available variables does not necessarily lead to improved forecasting performance, as redundant or weakly informative inputs may increase noise and reduce model stability. Therefore, the structures of the model input space is defined by selecting a subset, which specifies a particular configuration of additional input variables. The optimization strategy is based on the principle of the data-centric machine learning and treats the structure of the input space as the primary object of optimization instead of modifying the forecasting itself. The approach systematically evaluates alternative configurations of input variables. The algorithm of constructing the model in input space has the following steps. First, we define the target time series and historical window length. Then we specify the set of available additional variables. We construct a set of candidates input space configuration. And for each configuration, we form the corresponding input representation. Then we train a model using a fixed architecture and experimental setup and evaluate forecasting quality using selected metrics. Then we compare the results across all configurations and determine the optimized input space of structure. The workflow of the proposed approach is illustrated in figure on the slide, which demonstrates the difference between the conventional forecasting pipeline with a fixed input space and the proposed optimization-oriented procedure for constructing the model input space. Forecasting quality is assessed using standard quantitative metrics. The optimal configuration set is selected based on the aggregated forecasting quality measures computed across multiple error metrics and multiple forecasting horizons. When several configurations produce similar error values, preference is given to the configuration that demonstrates higher stability, reflected by lower variability of forecasting errors across different time segments or validation tools. The task of neural network-based forecasting of infectious diseases spread in Ukraine was addressed using normalized monthly time series constructed from reports of the Public Health Center of the Ministry of Health of Ukraine. In the Pacific study, a comparison is performed between the baseline forecasting approach and the approach with an optimized model input space. While all key experimental settings remain unchanged, in particular, the same neural network architecture and its temporal resolution, monthly time step, historical window length of 24 months, and forecasting horizon of 6 months, data processing and normalization procedures, training strategy, and evaluation metrics are preserved. This ensures that any difference in forecasting performance can be attributed solely to the optimization of the model input space. The dataset contains the disease category, the time index, and the indices indicator per 100,000 population. The X1 variable is the infectious category disease, the total number of categories, which is 57. The values are encoded as integers from 1 to 57. The X2 variable is the date observed period from December 2016 to January 2024. And the X3 variable is the incidence level, the cases. Prior to model training, the target time series were scaled using min-max normalization to the interval from 0 to 1. The exogenous variables defined unbounded scales will be used without additional normalization, while variables with arbitrary ranges were normalized separately. This preprocessing ensures numerical stability while preserving the semantic meaning of each variable. The normalization was performed separately for each time series over the entire observed period. Now, in the experimental part of the study, a limited set of exogenous data is considered to extend the model input space. These variables are not generated by the internal dynamics of the disease indices time series and are not used in the baseline neural network model without optimization. All exogenous variables are deterministic, derived from the calendar and demographic information, and available at forecasting origin, which reduces the risk of information leakage from future periods, as all variables are available at the forecasting origin. The selection of these variables is motivated by their known relevance in the epidemiological forecasting, where seasons patterns and population-related factors are among the primary drivers of disease dynamics. The following variables were also considered at the Z1 calendar month, and this from 1 to 12. It is used to account for intra-annual seasonal patterns in disease incidence. Z2, which is the season of the year, and from 1 to 4, and Z3, the normalized population size. In order to identify the most informative configuration of input data, a systematic enumeration of all possible subsets of the set in table on screen shown. In general, the input space optimization may be improved as a two-stage procedure, screening followed by the forward selection. However, in this study, the candidate set was limited to 3 exogenous variables. Therefore, the screening step was trivial and the optimization was implemented as an exhaustive enumeration of all subsets, which is equivalent. This design choice ensures a controlled experiment and allows for an exact solution to the input selection problem, avoiding approximation errors associated with the heuristic search strategies. As shown at the table on screen, the lowest forecasting error is achieved when using the configuration where we include all exogenous variables without prior selection, which does not yield the best result, indicating the presence of redundant features in the input space and confirming the necessity of the optimization procedure. The result presented in the table of performance of neural network trained on pooled time series indicate that the inclusion of exogenous variables reduces the approximation error on the training data. However, the greatest improvement is observed only when using the optimized input space configuration, which suggests that not all exogenous factors contribute equally to modeling the time series dynamics. These findings demonstrate the effectiveness of the data-centric approach to improving neural network forecasting performance without increasing model architecture complexity. Using the infectious disease incidence data, the baseline INBITS model demonstrated limited productive performance with an average forecasting error of 82% of MAPE. The inclusion of all exogenous variables reduced the average out-of-sample error to 78% MAPE, whereas the optimized input space achieved a further reduction to 73.5% MAPE. The sample evaluation also confirmed the positive effects of input space optimization. The average training error decreased from 63.5% MAPE of the baseline configuration to 57.10%. This approach improves model generalization and practical relevance while avoiding unnecessary increase in model complexity. And as for further research, it will focus on exploring automated and adaptive strategies for exogenous variable selection and integrating dynamic input space optimization into real space forecasting systems.